started? Good. Microphone's on, right? Yeah.
The microphone's been on the whole time.
It's okay. Battery's good. And I've got lots of more. I can change it. And I've got the microphone in the back when the Q&A starts.
Great. Great. Well, I mean, they may be asking questions during, so, okay, great. Do you want to check the position of the, whoops. Can you tell? Testing. Okay, is that good? It's on auto gain, or is it on a fixed? It's on auto gain. Okay, great. There you go. Great. Can you close the door in the back?
Yeah.
Yeah, great. Okay. Richard, do you think we should dim the lights or take the shades down a little, or what? Shades down just a tad. But yeah, you got to be careful with the.
We make it too much darker, we might have trouble with some of the pictures, but it's okay.
Yeah, I just don't want. Yeah, if we can dim the lights a little bit, that'd be great.
Okay.
Yeah, that'd be good. Yeah, not too much because they want to take notes, I'm sure, but just a little bit. Be good. Okay. Okay, so let's get started. So I just want to start my talk with kind of an outline or what I hope everyone will take away from this first lecture. First, I'm going to talk about light propagation across spatial scales. As I've mentioned, one of the objectives of this course is to, provide kind of a comprehensive approach of understanding what are the considerations when modeling light transport anywhere from the microscopic scale all the way to the macroscopic scale. And so we're going to talk about the various approaches for modeling light transport across spatial scales, talk a little bit about the applicability and the limitations of each of these modeling contexts, both theoretically as well as practically. And then I'll transition to talking a little bit about, from a modeling or computational perspective, what are the different considerations one has to consider when wanting to know something about light transport as it relates to a therapeutic application as opposed to a diagnostic application. Ultimately, the governing equations that you solve are the same, but the ultimate metric that you're interested in computing is different, and therefore the approach to doing that may differ. Then within a radiative transport context, we're going to introduce something called the radiance, which is kind of the primitive quantity that is the solution, in a sense, of the radiative transport equation. It is a six-dimensional object, which comprehensively defines the temporal, spatial, and directional characteristics of light transport. And we'll talk about how that can be derived and how that can be manipulated. And so that will kind of end the first part of the lecture, which will focus more on modeling and computation. And then the second portion will focus more on, I have one more element here, which is actually how you put together absorption and scattering processes in a way to extract what's called the radiative transport equation. And so we'll talk about how light propagation is modified separately by absorption and scattering and how both of these are treated in radiative transport. Then we'll transition to talking a little bit about the origins and characteristics and spectral dependence of optical scattering and absorption in tissues, where it comes from and how it can change depending on composition and structure. And then we'll combine these two elements, the elements of the modeling and light transport, with the intrinsic optical properties of tissue to derive fundamental spatial and temporal scales. And these spatial and temporal scales are going to be important to bear in mind because as we go forward in the course, when we consider optical penetration depths, optimal, say, spatial frequencies or optimal temporal modulation frequencies to actually extract optical properties, your sensitivity to absorption and scattering will be dependent on these fundamental spatial and temporal scales, which arise from a combination of the characteristics of light propagation and the characteristics of the composition and structure of tissue. And so it's that combination that gives rise to these spatial and temporal scales. So very basic, just want to remind all of you that there are two ways that we can model light. We can, in the classical description, light is a transverse electromagnetic wave where the electric field and magnetic fields are mutually orthogonal to each other, and both of these are mutually orthogonal to the direction of propagation. And typically, what we're interested in biomedical optics, broadly, if we're interested in wavelengths roughly in the visible and near infrared, both from a therapeutic and a diagnostic point of view. At the same time, one can also consider light from a particle or quantum description as localized neutral particles, which we call photons. And these photons have a quantized energy, which is linked to the wavelength. So the longer wavelength, the smaller the energy. And that's all parameterized through the speed of light and Planck's constant. Okay. Yet light falls that we're considering, it falls in a very narrow spectral band throughout the whole kind of panoply of electromagnetic radiation. And from the standpoint of biomedical optics, light in the visible and near infrared is actually quite special when you consider the relative spatial scales of the biological systems we're interrogating relative to the wavelength of light that we're considering. I'll talk a little bit more about that in a second. But also the corresponding photon energies are also very important, because the energies that we use when we use visible and infrared light are resonant with primarily the electronic structures of biomolecular molecules, as well as their vibrational structures. So that by doing spectral measurements, we're actually getting molecular fingerprints of the electronic and molecular structure of these molecules. And that's what makes it so powerful for uncovering tissue composition. So kind of zooming in from this very narrow rainbow here of wavelengths, I want to kind of talk a little bit about the spatial scales that we are interested in interrogating in tissues. And so this ranges all the way from kind of the micron or even submicron scale, which we use using optical microscopy, both conventional bright field and phase contrast, as well as these deep microscopy techniques, deep tissue microscopy techniques, where we can actually directly or indirectly get at subcellular morphology, subcellular composition, and then using various techniques, we can look at the coherence properties of light and how that gets modified by scattering to get more blurry but deeper imaging of deeper tissue structures using optical coherence tomography. We can look at moving scatterers to give us a sense of flow at larger spatial scales. Spatial scales roughly on the order of 10s to 50 microns at depth. And then we are also interested in how light is dispersed as it propagates into deeper tissue layers. And so techniques such as spatial frequency domain imaging and diffuse optical spectroscopy and imaging propagate deeper, collect light that is propagated more deeply into tissue and can give us some understanding of the interaction of cells with its surrounding matrix and vasculature. And finally, looking at very large volumes of tissue on the cubic millimeter or centimeter volumes to look at bulk tissue physiology and dosimetry. Now, when one is interested in interrogating tissues on these various spatial scales, it gives rise to various methodologies that one can use to model that light transport. Ultimately, these spatial scales down here, less than a few microns, are really dealing with light transport on spatial scales comparable to the wavelength of light. And therefore, to really understand that, one has to start from kind of the most rigorous model of light transport in a classical sense, which is Maxwell's equations. And we'll talk a little bit about that in a second, how much can be done and what are its limitations. As one goes deeper within tissue or looks at light transport over larger spatial scales on the order of roughly a few hundred, tens to hundreds of microns, one can start to look, throw away kind of the parameterization of light as a wave and really go to this ansatz of considering light as a neutral particle and go into the radiative transport regime. LS here designates the characteristic spatial scale of single scattering events, meaning what is kind of the mean distance that light will travel within tissue before it encounters a scattering event. And depending on the tissue, that's on the order of 10 to 100 microns, typically in the visible or near infrared. So the transition from needing to invoke Maxwell's equations to being able to get away with radiative transport really happens on spatial scales that are comparable to LS. Probably you want to be much larger than LS. So probably for spatial scales or tissue volumes larger than maybe 100 microns characteristic length scale, you can probably start to consider applying the radiative transport equation. But smaller than that, you really need to stick with the Maxwell's equation context. Now, once light has been scattered, often the change in directionality of that light isn't often modified that much. And typically one has to accumulate a number of scattering events before the photons have lost memory in some sense of its original direction of propagation. And once that happens, we consider light propagation to behave as a modified diffusion process. This is often called the diffusion equation, or I like to call it, it's really the diffusion approximation to the radiative transport equation. And this is a modified diffusion process. It's not exactly like thermal diffusion or other types of diffusion in that you actually can extinguish light. So you have to modify a diffusion equation to accommodate for absorption. And so this typically is valid on spatial scales that are larger than a transport mean free path. And we'll talk about what a transport mean free path means, but it essentially means that the light has to have accumulated enough scattering events such that it has kind of lost memory of its initial direction of propagation. And so this kind of maps onto the spatial scales that we're interested in biological tissue. So I want to talk about each of these three modeling approaches. So first in Maxwell's equation, so we know from high school, college physics that this is touted as kind of a rigorous model for electromagnetic wave propagation, and it can be used for propagation not only in kind of transparent media but also in turbid media. It models all wave phenomenon, interference, diffraction, polarization, and is accurate on pretty much all spatial scales relevant to us when dealing with biological tissues. The challenge with applying it in biomedical optics is really twofold. Number one, there's the challenge of how one represents the tissue as an electromagnetic construct. The two properties that characterize electromagnetic wave propagation are called dielectric permeability and permittivity. And these values and the spatial scales over which these values vary within a tissue system are often unknown. Okay? Although progress is being made in this regard. However, even if these are known, say that someone has figured out, how one can represent tissue rigorously within an electromagnetic context, to actually solve the equations is very computationally expensive. Progress has been made in the last 5 to 10 years in solving rigorously Maxwell's equations using finite difference time domain methods, pseudospectral domain methods, for very small volumes of tissue that are, roughly 50 to 100 micron characteristic length. But these computations take literally hundreds to thousands of hours on large clusters of computation. But there is a lot of interesting insight to look at fundamental impacts of cellular scattering on the dispersion of focused light beams, work done by Vadim Bachman at Northwestern as well as Andy Dunn at University of Texas at Austin. So all very worthwhile work. So if one really wants to understand, say how microscopy methods or even OCT on some level is really modified by scattering, one ultimately really has to double back and make sure that whatever approximate models that they may be using really stand up to the rigor of Maxwell's equations. However, if one is starting to look at spatial scales on the order of hundreds of microns to millimeters, one can start to think about using the radiative transport equation. So the radiative transport equation doesn't treat light propagation as waves, so it really has the transport of neutral particles. And the radiative transport equation is interesting in that it can be derived from Maxwell's equations with a number of assumptions, not all of which I will list here. But some of the key assumptions from a physical kind of more intuitive point of view is that each particle that scatters light in the medium must lie in the far field of the other particles, far field optically, meaning that when light scatters off of a particle, there's a scattered wave, and that scattered wave actually evolves with propagation distance away from that particle, ultimately becomes a spherical wave at a distance that's multiple particle diameters away from the particle itself. And you're assuming that each particle that may scatter light within the system lies in the far field of all the other particles. This is probably not strictly obeyed in tissue, yet we use this ansatz. Secondly, we assume that there are no correlations in particle positions. We assume a random media. And the reason why we have to assume that there are no correlations in particle positions is that if you had an ordered media with, say, repetition on a spatial scale comparable to a wavelength of light, you can actually sustain resonant wave propagation, and that's not, and sustain interference, which cannot be modeled within a radiative transport context. So this is a scalar model, not a wave vector model or vector propagation model that really cannot predict interference or diffraction effects. Yet one can modify it to handle polarization. And polarization can be handled using a transport equation, and we'll talk about this real quickly for each Stokes vector component. Stokes vectors are a way of representing the polarization state of light. It's a vector with 4 components. And one can modify the radiative transport equation to handle polarization if one solves for the various elements of the Stokes vector. And then, again, we can introduce additional assumptions, restrictions, approximations onto the radiative transport equation to make it still easier to solve. So the radiative transport equation, I should mention, is not trivial to solve either. Some progress has been made analytically. Monte Carlo simulations are often considered to be the gold standard for obtaining rigorous solutions to the radiative transport equation. And while progress is being made in using, say, adaptive methods to accelerate the speed and computational efficiency of Monte Carlo simulations, traditional Monte Carlo simulations, many of you may have experienced, can take hours to run. And so that has led the field, at least especially in the early days, to seek analytic approximations to the radiative transport equation that can be solved much more easily and much more rapidly. And these are known as the standard diffusion equations or the standard diffusion approximation or PN approximations. PN approximations are a little bit more general and more powerful than standard diffusion approximation, which we'll talk about in a sense. But what we do in these sorts of equations is that we form an approximate solution to the RT by expanding the solution, and what I mean the solution is the radiance, which I talked about, represents the spatial, directional, and temporal characteristics of light transport, and we expand that radiance spatially, or angularly rather, in a series of Legendre polynomials. And Legendre polynomials express spherical harmonics. They allow you to represent any function that lies on the unit sphere to arbitrary precision, as long as you're willing to expand this series out to order n. And the reason why we consider the unit sphere is because light propagation, any direction of light propagation, can be described as a direction from the center onto any location on the surface of a unit sphere. And so in general, the radiance can be a very complicated function on the unit sphere, and therefore to fully represent it, you have to take out this polynomial expansion to high orders. Now what this allows you to do is it allows you to reduce this RTE, which is an integral differential equation, to a closed set of n+1 coupled partial differential equations, which themselves can be solved. High orders still require much effort to be solved. And therefore, what we often do is that we usually take this series up to order 1, meaning we truncate after the first expansion, the first order expansion. And this leads to the P1, or standard diffusion approximation. And this has had a long history of development in biophotonics, going back to the mid-80s. And often still provide a workhorse for extracting optical properties in many applications. The limitations for the standard diffusion approximation are considerable, and one really needs to consider this. Number one, these predictions are accurate in highly scattering media. We'll talk about what that means a little later on, and at locations that are distal from sources and boundaries. And so we'll discuss what we mean by highly scattering and what we mean by distal locations in a moment. So I think I want to pause there because I'm going to switch gears a little bit. Any questions at this point? So this is meant to kind of discuss, what are the various approaches one can use to model. Often it's often interesting to consider the transition between regimes, and when one might be able to get away with a more crude approximation versus a more rigorous one. Everyone's okay with? Yes. So let's.
Can you actually reiterate those
Hold on.
assumptions when going? Oh. Can you actually reiterate going from those assumptions from Maxwell's to the radiative transport equation? Could you just explain those again? Thanks.
Yeah. So we're interested in modeling light transport in turbid systems that scatter. And so in a kind of strict sense, in a medium that is deterministic, that has structure, you're going to have scattering particles that are distributed throughout the tissue. And radiative transport equation, in some sense, takes a view that you have distributed scatterers at point locations throughout the system. So the first assumption means that the number density of particles is sparse enough such that the characteristic distance between particles is sufficiently large such that each particle lies in the electromagnetic far field of the other particles. So that essentially you have the far field approximation of the scattered wave is incident on any other particle. Secondly, that the particle positions within the medium have to be random, because if they're not random, you can actually sustain interference or diffraction over large spatial scales. In fact, a lot of pieces of optics, reflectors, are actually layers of thin films that are spaced at some multiple or half multiples of a wavelength, so that you actually get resonant features due to the scattering of light off of these multiple layers. So on a particle description, you want to make sure that the particles aren't arranged in an order such that you can actually sustain interference, because this does not consider interference at all. It's a scalar model. Okay, is that okay? Other questions? Okay. Great. Also, I encourage people, I know we have very well-trained electrical engineers and physicists in the room. So if there are other, in past lectures, we've actually had a lot of discussions, about, concepts such as this, because people in the room view these things from different perspectives, and often hearing those perspectives are helpful. Yeah, so Tom. Yeah, I'm goading people on Gordon as well in the back of the room.
I know this is maybe, more of a general philosophical
Yeah, sure.
question. Is anyone going even further back, which would be, quantum mechanical, because Maxwell's itself is a classical approximation.
Yeah.
But I'm assuming that, once you get into the area of singular molecular imaging and things like that, you have to start considering, quantum interactions.
Yeah. So I'll go and say, let me put quantum aside. I would say that there's still even great debate in defending RTE as a valid approximation or limit of the Maxwell's equation. I can refer you to a number of papers currently in the literature, because there's these assumptions of ergodicity issues with respect to, in Maxwell's equations, all the waves are propagating simultaneously and they're interacting with each other. Whereas here, we often in Monte Carlo simulations, we launch the photons individually and they don't interact with each other. So there are some fundamental issues here. Going from Maxwell's to RTE is not a trivial thing. And if you want to go into quantum mechanics, it's even the way that we represent photons is not consistent with the quantum mechanical description of what a photon is. So it's from a fundamental physics standpoint, these transitions are tenuous and challenging, because especially a lot of people are interested in hybrid simulations. There's a lot of work from many years ago looking at transition from radiative transport to diffusion, and can we develop hybrid models of stitching together a diffusion approximation at large depths within tissue with, say, a Monte Carlo simulation at close to boundaries. And people have done that, and that stitching is actually a little more defendable, because you could rigorously derive the diffusion approximation in the limit of the RTE. That same transition from Maxwell's and RTE is not as rigorous. Yeah.
I just find it fascinating that it's the same mathematics that kind of pervade all the models of it, right? So, we look at, quantum mechanics is dealing with particles, and the RT we're dealing with particles, but with particles of different characteristics. And then if you go to the diffusion equation, you talk about using the spherical harmonics. That's how we solve electron orbitals in the quantum scale.
Yes.
It's the same mathematical framework.
It is, yeah. Well, I think that could just be a more reflection of the limitation of our mind than anything more fundamental, right? We only have so many ways that we know how to represent the universe. Okay. Yeah, Tom.
When you say there...
Yeah, hold on. Let's just wait for the microphone. Thank you.
When you say there can be no correlations between particle positions, it seems like there are correlations when you get into the tissue.
Absolutely.
Lots of them in layers. And
yes.
There's protective layers, and there's changes between one tissue and the other. The collagen fiber orientations are change on a small scale. So these are all limitations.
They are, and I think people have recognized, say, if you try to shine light, say, on a tendon along the axis of the fibers, that is a difficult situation to model within a radiative transport context. Ultimately, when we talk about correlations, it is fairly stringent. They need to be correlations that are ordered and reproducible on spatial scales comparable to the wavelength of light. your cornea is a classic example. The spacing of your collagen fibrils are very tightly ordered between 54 and 58 nanometers. And the cornea the collagen in your cornea is the same collagen as in your skin. Yet this is completely transparent, and this is completely turbid. And it's because of that tremendous order that they have between the collagen. But it's the same collagen. Fiber diameters are slightly different, but the order is very high. So you can have tremendous different optical properties because of that. Yeah. Gordon, did you have something? Yeah. No. Okay. Good. I thought. Yeah. Okay. Yeah. Oh, hey, Rob. Yeah. Please.
Thanks. So, so you mentioned that the Maxwell's equations, trying to solve them, it's very, very computationally rigorous. But I know that obviously over the last couple of decades, a lot of work has been done with Monte Carlo simulations, as you also mentioned, where that's kind of gone from something that people also felt was really, really computationally rigorous to now it's at least seeming more manageable in a lot of cases. And I was wondering if there's kind of an analogous school of thought with the Maxwell's equations that eventually the computational burden is going to be reduced enough where people will be able to rely more on those.
Yeah. I can't claim to be an expert in that. I think, I don't know how much I can really comment. I think like I said, there are two issues. There is the computational burden, but there's also the representation.
Right.
How you actually represent the tissue. So let me just go back again. So some people may take issue with the fact that you can actually treat scattering as a wave hitting a discrete particle and then scattering off of that discrete particle, representing tissue like that at all. Another way one can represent scattering is that tissue has a continuously varying refractive index or a continuously varying permeability and permittivity, and it's that variation that gives rise to scattering. So how one, again, will represent the tissue, how you can get those properties, how you can represent the tissue now on really spatial scales of nanometers, because that's what's going to be important that can affect the actual wave propagation process. I'm sure there'll continuously be advances in computation, but there's also more fundamental issues. How are we going to extract the appropriate representation? Yeah. Okay. Shall we move on? Okay, great. Okay, so I mentioned that there may be different considerations in doing diagnostics versus therapy. Here's the laser pointer. I hope it's red. No, it's green. Oh well. Okay. So this is a really kludgy description of shining a red laser pointer on my finger, but of course this is green, so you don't see anything. But everyone's done this, I'm sure, in this room. And when you shine a red laser pointer on your finger, your whole finger glows red, right? And you see red light coming out. You probably, when you're a child, you go in a dark closet and shine a flashlight, and you see your whole hand glow red. Okay, and so there are two kind of things one can be interested in what's happening when you illuminate a biological tissue with a light source. One is if one can take a cross section of my finger and look at the light distribution, the light field, as you will, within the tissue, and this kind of color map just is diagramming the regions where there are a lot of photons impinging at a particular location versus areas where there's fewer photons impinging on the location. The rate at which photons are traveling from or traveling to any given point is given by the Fluence rate. This is kind of a power per unit area at any location. And generally, you're going to have some decay of this Fluence rate phi within that tissue. And this is really the metric that one is interested in if one is interested in some sort of phototherapy, whether it's a photothermal therapy You want to induce a temperature change. Whether it's a photochemical therapy, you want to make an inactive molecule photoactive. Or if you want to excite fluorescence, right? The efficacy with which you will be able to excite fluorescence is dependent on the photons that are available to promote that transition in that molecule from a ground state to an excited state so that it can re-emit. So intrinsically, if you're interested in therapy or fluorescence, you're interested in the internal light field. You're interested in the light distribution within the tissue. Now, when you're doing diagnostics or imaging, you're interested in a slightly different light field. You don't typically have access to this light field, although you might be very interested in it because you want to know where all the light that you're detecting comes from. But unless you have an interstitial probe stuck into the interior of the tissue, you only have access to the boundaries, whether it's the top boundary or the bottom boundary, right? And you can measure a reflectance or a transmittance in this simple geometry. Since you have effectively a collimated beam impinging, you typically measure some sort of decay on the lateral surface, either in reflectance or in transmittance. And so here, there may be some internal light field, but ultimately this internal light field, which is generated due to scattering and absorption within the tissue, gives rise to some field of light that is projected onto the surface. And so what this light field is on the surface is, pun not intended, it's a reflection of what's going on beneath the surface. So they're linked. Yet computationally, there are different considerations to extract one versus the other. So the question is that how does this light field get generated? Based on the fundamental interactions, okay? And it's all based on the experience, the trajectory of a photon or multiple photons that give rise to this collective light distribution. So very simply, if you have photons traveling within a tissue, what are the various outcomes for these photons? Okay, well, if you have refractive index mismatch, of course you can have specular reflection at the surface. Not all of the light you're going to deliver to the tissue actually enters the interior of the tissue. You can have some light that undergoes one or multiple scattering interactions and get re-emitted. We typically refer to light that has undergone one or more scattering interactions within the tissue and then escaping a diffuse reflectance in this case because it's coming back through the same surface that the light came in. You can also have light undergoing some scattering but then running into an absorber. Here I've shown the absorbers discretely, but they could be distributed homogeneously within the tissue such that the light gets extinguished gradually as it propagates. You can also have light transmitting after multiple scattering events or directly through. Or you can have, of course, absorption that leads to fluorescence as well, and then the re-emission is at a different wavelength, and then you have to consider the propagation of that light through the tissue or even transmitted or reflected out. Okay, but collectively, you do hundreds or thousands or millions of these photons, and you can generate this light field. And this is again just an artistic description of what the light field may look like, which is kind of consistent with our intuition. It's a homogeneous medium. But what I want to emphasize here is that this color coding is kind of telling you, well, what is the mean number of photons that are emitted from this particular location. But this is not the complete story. What's really important is not just how many photons are available at this location, but what is the directional distribution of these photons? In what directions are these photons traveling? And the representation of that is called the radiance. So the radiance is a function that's not only a function of space, denoted by bold r, which is just a vector denoting this location, but direction, which we denote by capital omega, and time. Time is to just consider the fact that our light source may be varying in time. So if we just kind of look at this point, we may just, intuitively, it seems like you probably have more light going in this forward direction, given that you have all of this collimated light coming in this direction. You may have some light moving backwards because there's a lot of scattering in here that probably sends light back, but probably not as much as light coming forward, since you have more light at locations up here traveling downwards than you have light coming up. And of course, this is just a two-dimensional cross-section, right? There's also light coming into and out of the board, right? It's directions on a unit sphere. So ultimately, the complete solution to this problem can only be derived by finding the solution to this radiance. This radiance is generated through all of these various interactions, and we'll focus primarily on the interactions of absorption and scattering separately, and then we'll put it together to derive the radiative transport equation. Okay, so how can radiance be changed or diminished through absorption? Well, this is kind of the classic derivation of Beer's law. So let's just consider a radiance existing at location S, which is going to be this surface on this differential slab, propagating in a given direction omega. So all the direction, we're considering only one direction omega, which is going from left to right. If you have a differential thickness here, you're going to have some extinguishing of this light field due to absorption, and you're going to get a different light field. Everything is going to be traveling in the same direction because absorption doesn't modify the direction of light. You're just going to have less of it coming out on the other side because you've lost some of the light, but it's all in the same direction. So the change of this radiance per unit distance s is going to be linked by the density of absorbers times the actual amount of light coming that you're directing into this sample. And of course you have a negative sign here because the absorption diminishes the light. If you separate variables, you bring all the L's to one side, you bring the S on the other, you integrate, you get classic Beer's law. Okay? Mu A is an absorption coefficient. It has units of reciprocal distance. So it's kind of what is the mean number of absorption events you're going to have upon traveling a millimeter, number per millimeter. And this is kind of classic Beer's law. And the nice thing about absorption is that once they've been absorbed, you don't have to worry about them anymore, right? They're gone. They may produce a temperature rise, they may produce fluorescence, but that's at a different wavelength. We're not interested in that right now. So you forget about them. So absorption is easy. Scattering is a little bit more challenging, okay? Scattering, you can also represent the radiance in that same direction omega using the same sort of Beer's law, right? You have, if you're interested in the light propagating in the same direction, it also gets diminished by some coefficient. Here we call it mu s, representing the density of scatterers. And you can generate the same type of Beer's law. Remember, we're only considering the light propagating in the same direction as was incident. But the problem or the challenge here is that the photons haven't gone away. They're just now propagating in different directions. And so this diminishment of light from this given or this direction omega that we're interested in now populates the light propagating in other directions, and we have to keep track of that. But if you're interested just in collimated light, you know you're going to have diminishment of the collimated light due to both absorption and scattering. So the total attenuation of light traveling in a specific direction can also be expressed by Beer's law, where mu t is simply the sum of mu a and mu s. This is sometimes called the total attenuation coefficient, mu t. Okay? So the question then is that how do you now deal with these other photons that are propagating in a manner such that we're not only able to predict the radiance traveling in a given direction omega, but traveling in all directions omega that you may consider. And that's where we go to the radiative transport equation. And so what I want to do is I want to spend a little time unpacking this equation so that people don't feel so intimidated by the upside down triangles and the integral signs and the arrows and all this stuff. It's just a very compact language, but it should be intuitive. So we're going to treat the general case of radiance that is a function of position, direction, and time. Okay. Maybe before I do this, I want to make sure everyone's okay with the concept of radiance. Any questions about radiance? because I know that when I first got into this field, this took a long time for me to really understand, because I actually came with a heat transfer background, and I loved diffusion, and I knew temperature. Temperature is a function of time. It could be a function of space, but now we have direction. And it adds a tremendous amount of complexity to this whole problem. So, I just want to leave that as an open question. Does anybody have a question about it right now? I'll show in detail how we can manipulate the radiance and how we can go from radiance to fluence rate, which is something that people are more familiar with. But I'll leave that as an open question. At any time during this lecture or future lectures you have a question on what exactly radiance is, please raise your hand, because this is a very important concept. Okay? So here we're going to consider radiance at a particular location R in a particular direction omega. Okay? And yes, okay, so we do have a question. So let's do that. Excellent.
I mean, exactly what you said. I'm not used to thinking in terms of unit direction.
Yes.
Does that basically mean, if we use Cartesian coordinates, that it's really 3 equations and we have to consider every direction to fully describe what's going on?
Yeah, so typically as I referred to earlier, in the diffusion approximation, we actually think about light traveling on a unit sphere. So actually, when it comes to direction, we don't use Cartesian coordinates, but we use spherical coordinates, and you'll see this in just this moment. So there's R, which you could use whatever coordinate system you want. You could use the spherical coordinate system, you can use Cartesian, you can use cylindrical. But typically for omega, we typically look at unit sphere. Jerry, do you have any comments about that? Is that typically always, you haven't seen?
So,
okay.
We represent the sphere in 2 dimensions and its surface, the unit sphere.
Mm-hmm.
So these
Right.
are normalized to have length 1.
Yeah. Okay. And so in that case, you have two directions: the azimuthal and the longitudinal angle, theta, phi, and theta, which we'll see in just a moment. Okay. Any other questions, Gordon?
I really just had a comment. There are lots and lots of optical units for measuring perhaps what people would call power and its directionality.
Yes.
And so there's radiance, but there's also irradiance, and it's worth noting that there's a difference between those two and not to get tangled up in them.
That's right.
So radiance has this angular dependence, which you always have to keep track of, and that's the difficult bit, I guess.
That's right. Yeah, irradiance usually is the amount of light or the power that's impinging on a flat surface. And so, and we'll see that again, because what we'll be showing, I talked about therapy and diagnostics, and how in diagnostics you're interested in a reflectance or a transmittance, and ultimately you're looking at the light that can be traveling out of the tissue at multiple angles, but ultimately you're only detecting what hits a flat surface. And so you've got to figure out how all of this light that travels in different directions gives rise to a reflectance, which is basically an irradiance. Yeah, but that's a very important point. And, but we'll look at how we handle that mathematically. Okay, so here we have a time rate of change. V here is just the velocity of propagation in the tissue. So this is going to be V is just the speed of light divided by the refractive index of that tissue, which typically we use 1.4 is kind of a traditional value that's used for refractive index of tissue. And this is, how, if we're considering this point within the tissue denoted in green, how is this radiance changing with time? Okay? And it can change in time through multiple interactions. So first we have to recognize that light is constantly moving, right? So, and therefore you can have loss of light or gain of light through propagation, okay? And this is a directional derivative. This is the gradient, spatial gradient of the radiance, dotted in the direction of propagation, omega. So this basically says, how much light do we have moving into or out of that volume in the direction omega that we're considering, okay? And so this is, if you have light propagating in omega, it's propagating away from this location. Therefore, you have a loss of light due to that propagation away. Okay? So this is just the spatial gradient of L, because L is defined spatially amongst all R, and you're taking the dot product of that onto the direction that you're considering. Okay? You can also lose light out of direction omega due to an interaction. That interaction can be through absorption, right? We know that if you have absorption, the light's gone. You could also have a loss of light from omega due to scattering, right? Because the scattering takes the light from omega to a different omega, which is dealt with a different equation. It'll be another direction. But out of omega, it can also be lost due to scattering. So mu t is this transport coefficient or total interaction coefficient, is the sum of mu a and mu s. Okay, so you have a loss there, you have a negative sign there. Okay, so these are the two ways you can lose light, right? Through propagation and through interaction, absorption or scattering. You can also gain light, right? You can gain light by, you can have a photon traveling, so we're interested in this omega here, going from left to right. Well, you can have other light in the medium that is propagating, going along its merry way, and then hits a scatterer and gets scattered into the direction you're considering. So this term here considers, well, we have all of this light that propagates at these different directions, omega prime. What is the probability that that light will be scattered from this direction omega prime into the direction omega that we're considering? Okay, so there's this function which is called the single scattering phase function, which is a normalized probability density function that describes this probability. Okay? And since there's not only one omega, so this product tells you, well, of the amount of light that is available at omega prime, what is the probability that that light will get scattered into omega? Okay? So this product tells you the transition from omega prime into omega. And you want to consider all the different omega primes. You have all the omega primes along the unit sphere, right? You have to consider all these other angles. So 4 pi just means that we're integrating over 4 pi solid angle, which is the surface area of the unit sphere. And then we have to multiply this by mu s, because if there's no scattering, if mu s is 0, well, we're not going to get any of this light going from omega prime to omega, because there's no opportunity for scattering. So the amount of light you actually get into omega depends on the amount of scattering in the media. So this is a gain through scattering from other directions. And then you can also have optical sources in the media that provide light at particular locations in particular directions. So the radiative transport equation is just a conservation equation, making sure you're bookkeeping, making sure that you're accounting for all the light through scattering or absorption. Okay, let me pause there and see if there are any questions. Everybody's fine? Okay, fine for now at least. Okay, good. So the other thing I just wanted to mention, I alluded to this earlier, is that one can account for polarization within a transport context. And this is just the vector radiative transport equation. It's the same form, only I've just replaced the L's with I's, which the I is representing the Stokes vector, bold I. And then the phase function it has a generalized form because you have to have a different phase function for each of these polarization components. So there's the electric field parallel and the complex conjugate of the parallel component of the electric field and then perpendicular here. And then you have IQUV, which collectively describe the polarization state of light. And Z is called the scattering matrix, which essentially is, again, has 4 components that describe the transition of light upon scattering IQUV to a new IQUV upon scattering. So it's actually a 4x4 matrix, because you can have transitions from any component to any other component upon scattering. Okay, so it's just a more complicated, complete way of doing radiative transport when considering polarization. Okay.
How many variables are we up to now?
You can count. We can do that over lunch. Okay. 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 So now, so none of you, I mean, all of you guys work in biomedical optics, but we typically don't look at radiance, right? We look at, diagnostic. You look at an irradiance or a reflectance or a transmittance. Even in therapeutics, you typically look at fluence rate. You want to know what is the total amount of light that's coming, impinging at a particular location. And so how do we compute those? So from the RTE solution, so the solution to the RTE and what ultimately a Monte Carlo simulation will give you actually is L. You can, if with the appropriate design of a Monte Carlo simulation, you're not limited to only getting the internal fluence rate and the reflectance and the transmittance. You can actually get the full radiance, the full angular, spatial, temporal description of light propagating in that medium. But once you have L, you can get access to all these other things. So let's first look at therapy. If you're interested in the internal light field at this location, how do you get it from the radiance? Well, the fluence rate, which we'll denote as phi, it's a function only of position and time. It's not a function of direction, right? It's just the total amount of light that's actually being emitted from this location. And this is simply an integral over the unit sphere of the radiance. So we got to integrate over all omega. So as I alluded to with the question from Tom, what coordinate system do we use to represent direction? So we use spherical coordinates. So the unit sphere, any location on a unit sphere can be denoted by two angles. So you have the angle theta. So let's just say that light is propagating from the bottom of the screen to the top. So Z would be into the medium. So say we have a photon traveling in Z. It can be altered from its path through scattering by a deflection off of the Z-axis, okay, theta. And then it can also be scattered out of or into the plane of the board, right? And that is phi, that goes around the XY. So theta is typically referred to as a polar angle, and phi is referred to as an azimuthal angle. And so a unit area on the unit sphere, well, this arc here is given by a delta theta. And if you're going around the z-axis, when you're going around in the phi direction, the radius of that circle is given by r sine theta, but since we're considering a unit sphere, the r is just 1, so sine theta. And then the circumference of that arc is given by sine theta delta phi, okay? So if you expand d omega into spherical coordinates, this integral ends up being a double integral. Phi, at any theta, you want to go around the whole circumference of the unit sphere. And theta goes essentially from theta equals 0, which is collinear with the z-axis, all the way down to the negative z-axis, which would be theta equals pi. So your limits of integration are 0 in phi from 0 to 2 pi, and in theta from 0 to pi. And again, the differential area is given by d theta, which is this arc in theta, and sine theta delta phi, which is going to be this top or bottom surface of this little differential area element. So if you do that, you're integrating this L over the unit sphere. Okay? Questions about that? Okay. Analytic geometry from high school. Maybe. Okay. So I remember in past workshops saying, well, are you assuming that the light field is isotropic? And the answer to that is no. So L, again, has different value for different omegas, as denoted by the different magnitudes of these arrows. If you replaced L with a constant, that would mean that you're dealing with an isotropic field, right? You're assuming the same magnitude in all directions, okay? But it's this directional dependence that allows you to take care of any angular variations of light propagation. Okay, so now the question is that if you're interested in imaging or diagnostics, you don't have access to this internal light field. You only have access to what's coming out of the surface. Okay? So this is a depiction of that graphically. I just want to note that typically you have a refractive index mismatch at that surface. And so I've introduced intentionally a discontinuity in the magnitude of this radiance, because that's what happens. And we'll consider the boundary conditions a little later. But when you're looking at a reflectance or an irradiance at the surface, you're interested only in what's happening at z equals 0 in this case, and you're interested only in the light that's traveling upwards. So instead of integrating over the entire unit sphere, we're only looking at the directions that are, in this case, propagating in a direction that is in the hemisphere opposite of the tissue hemisphere. So you have to take the direction of the light propagation dotted with the inward pointing unit normal, and if that is negative, that means you're propagating away from the tissue. Okay, so this means that you're only integrating over a hemisphere. And you're looking at the light, the radiance that is propagating at z equals 0 just on the other side of the boundary, not the tissue side, but in the air side, so to speak. That's why I have a z equals 0 minus. And we'll talk about how we can get that. It's also a function of angle, and in theory time. And then what you need to do is that the reflectance, typically your detector is not a sphere. Your detector is a planar surface. So what you need to do is that you need to take this direction of propagation, and you have to take the projection of that onto the outward pointing normal. And since I've defined the inward pointing normal as z, I have to take the projection onto minus z. And so, of course, even if the amplitude of this arrow was the same as the amplitude of this arrow, light traveling at this more oblique angle is not going to have the same contribution on your planar detector as light traveling normal to that surface. And so this accounts for that. Okay? Now, if you had a detector that was hemispherical, then you don't have to worry about that dot product because you're capturing light normal to that detector at every single location on the unit sphere. Okay? But typically your detectors are planar. Okay? So that's how you extract reflectance. And so the integrals, sometimes in some geeky transport literature, instead of showing this dot product less than 0, they just say S2 minus, which is the upward pointing hemisphere in the negative z direction. So I just thought I'd throw that in just in case you run into that and are confused. And then the limits of integration are slightly altered here. Again, theta is defined in the forward z direction, so the theta, limits of theta now start from pi over 2 to pi. And the phi is still 0 to 2 pi. For every theta, you're going around the whole unit sphere. Okay? So that's what that integral looks like. Okay, so let me stop there. I'm going to switch gears. We're going to put aside light transport for a moment and talk about tissue properties. Any questions about this? Okay, good. Everybody's still awake. I consider that an achievement. Okay, good. Monday morning, dim lights. Okay. Okay, so let's talk about scattering and absorption in tissue. So what's really interesting is that a lot of the structures we're interested in cells and tissue have spatial scales that are comparable to the wavelength of light. And therefore we are intrinsically sensitive to variations in tissue structure and composition on spatial scales comparable to the wavelength of light. This is a kind of now very famous figure developed by Steve Jacques. Tom probably saw it at an earlier workshop. Yeah, showing kind of the multi-scale nature of structures within tissue, ranging from tens of nanometers in the form of lipid bilayers, all the way to cells which have characteristic spatial scales up to tens of microns. And so, you really have a 3 orders of magnitude variation of spatial scales that represent the structure of tissues. And the visible spectrum of light is right in the middle of all of this fun, right? And so typically, though, we have structures that can be comparable or much smaller than the wavelength of light, and there are also structures that are, I would say, larger, but not tremendously larger. You'll see that actually here, there's a lot more structures that are of interest that are much smaller than the typical wavelength of light than there are larger. One of the cellular components that are of great physiological interest is mitochondria, and mitochondria itself has a spatial scale on the order of a micron, but then within the mitochondria there are all of these membranous structures that have spatial scales on the order of tens of nanometers. Okay. Now, as we know, tissue is not just cells, it's also matrix and vasculature. One of the most important matrix components is collagen, and collagen in itself has a hierarchical structure with striations going down to tens of nanometers, actually, all the way to how they're packaged into collagen fiber bundles that could be as large as a few microns. And how these structures scatter light are related to the characteristic spatial scales and the refractive index variation. And we're going to talk about that next. So from a fundamental perspective, from a wave transport perspective, we have to deal with electric fields. And essentially, to transition from an incident electric field to a scattered electric field, one has to do a transformation based on what's called a scattering amplitude matrix. And we'll see this tomorrow in Janika's talk. But essentially, the scattering amplitude matrix tells you how, if you have a planar wave impinging on a scatterer, how the parallel and perpendicular components of that electric field oscillation get modified in angle, both polar and azimuthal angle, in the scattered wave. So it gives you the full angular variation of the scattered wave based on the incident wave and the characteristics of the scattering amplitude matrix. And the scattering amplitude matrix is dependent on the object that is scattering, okay? And this is for a general particle that doesn't have any sort of symmetry, okay? It does simplify for spherical scatterers. Now, we're going to be interested in how we can, since we're focusing more on radiative transport, we're interested ultimately in how we get mu-s. Mu-s is the object that we use to parameterize the scattering properties of tissue. And so here's what I want to show you how we get to mu-s from this messy scattering amplitude matrix. So essentially, just consider a case where we have a planar wave impinging on a scatterer. This incident wave continues to propagate. There's some sort of scattered wave which combine, and then you say you have a detector that is collimated with the incident light field. There's a parameter called the scattering cross-section, which is defined as the area of an index-matched, perfectly absorbing disk necessary to produce the measured reduction of light. So in reality, this particle has a different refractive index than the surrounding medium. Otherwise, it wouldn't scatter the light at all. It would just go right through. But what we're trying to find out is that if I replace this by like a microscopic hockey puck that is black, that will absorb every single piece of light, how large does that hockey puck need to be in order to get the measured reduction of light that you see when you put the particle there? And so that's what we do here, is that essentially we look at the ratio of the power, which is linked to the intensity, which is linked to the square of the electric field of the scattered wave over the incident wave. That's the reduction of light. You have to actually look at this over all angles. It's not just in the collimated direction. And this is equal to a scattering efficiency times the area of that disk. So this is times the area of the actual scatterer. So this is the scattering cross-section. This is an area. It's given because you have a square of the wave vector there. And so this scattering cross-section can be decomposed into the scattering efficiency and the actual cross-sectional area of the scatterer. And so you can imagine that the scattering efficiency takes on values actually from 0 up to 2, actually you can have disks that need to be twice the size of the scatterer in order to actually accommodate for the measured reduction of intensity. And that's because the particle can absorb, but it can also scatter. And so you can have losses due to both. The scattering coefficient is derived by the scattering cross-section, which has units of area, times the number density of scatterers, which has units of number per unit volume. So that's how you get a unit of reciprocal length, okay? And the reciprocal of mu s represents a scattering mean free path for photon travel. So this scattered wave intensity ultimately is given from this computation, right? So essentially how this scattering amplitude matrix gives rise to a reduction in scattered electric field essentially gives rise to this ratio, which gives rise to this scattering cross-section. So the scattering cross-section is just a parameterization, it's a condensation. You lose a lot of information about the nature of the scattered field by just considering the scattering cross-section and mu s. So now I want to just chat about how do these scattering amplitude matrices look like. And I'll focus on unpolarized light, so I'm going to kind of combine the parallel and perpendicular polarization and just look at the total intensity. And I want to first consider particles that are much larger than the wavelength of light. So in the biological context, these are things like collagen fibrils, for instance, or even mitochondria. So this is an angular distribution of light scattering at 650 microns of a water droplet with the radius of 10 microns. So it's a fairly large particle in air. The light is propagating from left to right. And what I want to note are two features. Number one, that this is on a logarithmic scale. So this is a polar plot. Light going from left to right. You see that there's a peak directly at 0. So, and everything else, all the other angles are much smaller. In fact, you can see that most of the light that's scattered in other directions are, let's see, 1, 2, 3, roughly 3 units lower. So that means that this backscattered background is about 1,000th of the forward scattering background. Most of the scattering is strongly forward scattered. The other thing I want to emphasize is that this is very structured. You see how many ripples, undulations there are. And this is because physically, the wavelength of light here is 650 nanometers. The particle is 10 microns. So you can imagine you have this huge particle and you have this wavelength of light which has a lot of oscillations. If you freeze frame the light, superimpose the light waveform on top of the particle, there are probably what? Let's see, about 13 cycles of that wave in that particle, which means if you decompose that particle into dipoles, at any snapshot in time, all of these dipoles in the water molecule have different orientations. And they're oscillating out of phase with each other. And so in the far field, when you look at any one angular location, the propagation in the far field of these individual dipole moments are going to exhibit tremendous constructive and destructive interference. And so this rippled nature is due to the fact, it's directly related to the fact that the wavelength of light is much smaller than the particle size. And so whenever you have that situation, you're going to have a lot of constructive and destructive interference. You're going to have a very structured phase function. So this is actually the single scattering phase function for this water droplet, okay? And tissue, if you have collagen, it won't be as rippled as this, but you will have, number one, tremendous variation in drop in this backscatter relative to forward scatter, and you're going to see a lot of structure, okay? The other thing I want to point out is that the amount of the scattering coefficient is weakly dependent on the size of the particle. You know, the power is to 0.3. It varies depending on the situation. N is the relative refractive index of the particle relative to the surrounding media. And I'm sorry, this is just the refractive index of the particle, excuse me, it's not the relative refractive index. Lambda is the wavelength. So here you also see that the scattering coefficient is gently varying with wavelength. It's falling very gently with wavelength. And this approximation, given from this reference, is fairly good for many biological particles. So the key thing is that the angular distribution of scattering light is highly forward directed and displays very fine structure. Okay. Now, if you consider a smaller target, a target where the particle size is much, much smaller than the wavelength of light, you get the Rayleigh limit of Mie scattering. So Gustav Mie was the first person to solve Maxwell's equation for a spherical scatterer. Okay, and when the particle is much smaller than the wavelength of light, you get the Rayleigh limit. Here I'm showing this single scattering phase function now on a linear scale for two polarizations of light. For the P and S polarization, P is the electric field parallel with the plane of the board. S is for the electric field perpendicular to the plane of the board. And so you have, first in one case, a lobed structure where the electric field is oscillating in the plane of the screen. And then you get this perfectly isotropic structure for the S polarization perpendicular. And then this green is this average between the two if you're dealing with unpolarized light. So there are two things here. Number one, you don't see as much structure. Remember, this is on a linear scale. These variations are fairly smooth, even though you do have this very strong lobe structure. The other thing is that you have equal amounts of light scattered forward and backwards, okay? As opposed to Mie scattering, where most of the light is all scattered forward, okay? The other thing is that your variation in your scattering cross-section is much more sensitive to both the size and the wavelength, right? So here you're actually scales with the square of the volume. It's the radius to the 6th power scattering cross-section increases. And you are highly damped in wavelength. So you have 1 over lambda to the 4th dependence of Rayleigh scattering. And this is the classic explanation for why the sky is blue, right? You have much more, you have all these very small particles in the atmosphere. You scatter much more blue light than you do red light. Okay, so here the angular distribution is symmetric. It is symmetric, meaning you have equal amounts of forward and back scattered light, and it varies gently with a polar angle. So what does this mean for tissue? Okay, tissue is a virtual potpourri of scatterers, right? You've got scatterers of all types with different refractive index mismatches to different sizes. So there are a couple things that we do. In the transport equation, we look at μs and the phase function. So we need to know what the number density of scatterers are, and we need to know the angular distribution. In the diffusion context, we actually don't even see μs. We see something called μs prime, and we'll see that later on when we derive the diffusion approximation later on in this course. But you see what's called the reduced scattering coefficient, which is the product of the single scattering coefficient μs times 1 minus g. G is something called the single scattering asymmetry or anisotropy coefficient, and it's the average cosine of the scattering angle. So what this means is that for theta going to 0, where there's no scattering, G becomes 1. When scattering is perfectly isotropic, the average scattering angle is actually 90 degrees, right? So G is 0, right? You have equal amounts of light going forward or backward. If you have a particle that somehow scatters more light backward than forward, you would actually have a negative G. The reason why μs prime is helpful is that it brings particles which have different phase functions kind of on an equal playing field. You see that you may have a large μs, you may have tons of particles, Mie particles for instance, that give you a large μs, but if their G is very, very high because they all scatter forward, they have a G close to 1, they don't do a very good job in randomizing the direction of the propagating light because it only deflects the light very moderately. But if you have a lot of Mie scatterers, their Gs are going to be much smaller because they basically scatter equal amounts of light forward and backward. They actually do a much more effective job in randomizing the light propagation direction. And so μs prime kind of is a way of putting the scattering effectiveness of different types of particles on the same playing field. And that'll be very important. And tissue typically is modeled as a mixture of Rayleigh and Mie scatterers. Often in the literature, what you see is that you see empirical correlations of the wavelength dependence of scattering in tissue as an inverse power law to wavelength. We saw that scattering typically declines with wavelength. And what they do is that they use A as some sort of density number of scatterers, and then you pick what is the μs prime at some reference wavelength. Sometimes it's chosen at 1,000 nanometers, sometimes 500. And you have some sort of decay according to B. So sometimes they do a single power law. You can be a little bit more sophisticated and say, well, I know that I have some number of scatterers in my tissue that are really small. So a fraction of my scatterers in tissue are Rayleigh scatterers. We'll call this the Rayleigh fraction. The rest of them are not Rayleigh scatterers, they're Mie scatterers. And so these Rayleigh scatterers should have a lambda to the -4 dependence. These other non-Rayleigh scatterers, Mie scatterers, should have a different dependence, a different value of B. Can I fit my measured wavelength dependence of reduced scattering to get the fraction of Rayleigh and Mie scatterers and get a slightly different value of B? So what this plot is from Steve Jacques' recent paper in Physics and Medicine and Biology, where he maps reported values for B and B Mie. If B Mie equals B, it means that there are minimal Rayleigh scatterers in the material. So tissues that lie on this 45-degree line, it indicates that they basically, F Rayleigh is basically 0. And the further deviation you get from this 45-degree line indicates the higher prominence of Rayleigh scatterers in that tissue. And here you see the correlation between the difference. If you have B Mie should be probably smaller than B because you've extracted out all of the Rayleigh scatterers. How this reduction in this value of B due to separation of the Rayleigh scatterers maps to the actual number of Rayleigh scatterers in that medium. So you can get more information from this reference. But this is a very helpful compilation of tissue optical properties and how they relate to this conceptual framework of considering tissue as a combination of Rayleigh and Mie scatterers. And of course that tells you something about the wavelength dependence, and there's also the amount of intrinsic scattering in various tissues, and this is just the value of A for various tissues compiled again in this publication. But you can see that it varies considerably about, you could see probably a factor of 6 or 7 going from skin, dermis, epidermis at the top, which are very highly scattering, to tissues such as breast, which is very low scattering relatively. And then there are also considerations of what the phase function looks like, and these are values as a function of wavelength for various tissues of the single scattering anisotropy, how much forward directed that scatter is relative to, say, a Rayleigh context or a Mie context. And this, in various models, we typically use the Henry Greenstein's scattering phase function, which is an analytic phase function that can kind of give you an approximate angular distribution of light depending on this G value. Okay, so we're in the home stretch here. Just want to talk a little bit about absorption. So the first thing that one has to be really aware of when looking in literature trying to extract values for μA, the absorption coefficient, is that there are kind of two different conventions for absorption. Especially when you're looking at molecular absorption, you're probably going to a chemistry text, and they use slightly different metrics. So here, the classic measurement of absorption is you look at the amount of transmission coming through with an incident intensity and a transmitted intensity, and the transmittance is just the ratio of the transmitted intensity relative to the incident intensity. typically this is, in chemistry and spectroscopy, often this is expressed as 10 to the power of some extinction, or optical density, rho. The optical density rho is a product of the molar extinction coefficient, which has units of inverse length and inverse concentration, molarity. The concentration of the formulation you have, and the optical path length. Okay, and so often when you go into chemistry texts, what they give you is not mu a, but they give you this molar extinction coefficient, and you have to take care to correct for this molar extinction coefficient if you're dealing with a equation that uses mu a. Mu a comes out of more of a physics pedigree, kind of an analogy to scattering, where you look at transmittance as an exponential with base E, and you assume an absorption cross-section times the number density of absorbers. So it's more like a particle description of absorption as opposed to a solution description of absorption. And here, mu A is just a product of this absorption cross-section number density. But if you want to convert from one to the other, from epsilon to mu A, you have to multiply or divide by the natural log of 10, which is an important factor. It's around 2.5 or so. So that's important to not make an error. So in tissues, you have a vast scale of absorption coefficients. Here's an absorption spectra for relevant chromophores in tissue over a fairly broad wavelength scale from the vacuum ultraviolet all the way into the infrared. Typically, we operate somewhere between 400 here to anywhere maybe to 1200 here. Prominent absorbers in the visible and near infrared are oxy and deoxyhemoglobin and melanin. Although if you do any experiments or do therapy in the near visible ultraviolet, you have to deal with DNA, with protein, and in the vacuum ultraviolet, you actually have a lot of absorption by water. If you go out further in the infrared, water becomes a problem as far as absorption is concerned, or it doesn't become a problem actually. It's interesting to probe states of water within tissue. One thing I haven't listed here is lipid, which also has some vibrational absorption peaks here. Far out in the infrared, you have some collagen signal. What's important to know is that absorption is very large in the ultraviolet, in the near visible, and in the infrared, and absorption is very low in the red and near infrared, and so that gives rise to deep tissue imaging and also for therapy. What's also relevant for modeling is this ratio of scattering to absorption, because the ratio of scattering to absorption also tells you a little bit about how valid it is to use the diffusion approximation. So this is a plot of this relative ratio of scattering to absorption. You see again in the visible, things are low. This is 1 here. So here, absorption and scattering are comparable. But once you get to about 600, you start to see this tremendous rise in scattering. And that's because you have a drop-off in hemoglobin absorption. These two peaks here are due to the Sorey bands of hemoglobin. So here is the visible. You still see that you actually have, a fair amount of absorption relative to scattering here. But now, as the absorption of hemoglobin wears off, you get tremendous penetration due to a scattering-dominated situation. And then here you start to see the absorption of water creep in, and now you start to see absorption becoming more important. And so the reason why I put up this slide is that this naturally shows you where kind of the diagnostic or therapeutic window is. It's really where you see this dramatic increase in this ratio of scattering to absorption. It also is the regime where the diffusion approximation is probably a reasonable approximation in many cases, but not in all cases. It depends on where you're probing the light field. And certainly when scattering is comparable to absorption, you really need to resort to Monte Carlo descriptions or radiative transport descriptions. And then finally, to kind of put things together, I said that the combination of the optical properties and the transport of light gives rise to important spatial and temporal scales, which will be very important when we talk about spatial frequency domain imaging and temporal frequency domain imaging, which is characteristic length scales for absorption, which we've linked to, and scattering, which are linked to the reciprocal of the absorption and scattering coefficient and the reduced attenuation coefficient. L star is a transport mean free path, which is 1 over the sum of mu A and mu S prime. So it's the characteristic length scale for a photon to encounter an isotropic scattering event or absorption. I have typical values here. Light typically has to travel hundreds of millimeters, if not more, to encounter an absorption event on average, whereas the typical spatial scales for scattering are much smaller. And this gives rise to temporal scales. Photons last a long, long time in tissue before they're absorbed. And so you can extract a typical absorption time, this is often called the absorption relaxation time, by taking the reciprocal of the absorption coefficient and multiplying it by the speed of speed of light in the tissue. And the typical values for photons to hang around in tissue before they're absorbed are on the order of hundreds of picoseconds to tens of nanoseconds. This is to be contrasted by the time it takes for a scattering event to occur, which occurs really on the femtosecond timescale due to the density of scatters in tissue. And so the characteristic timescales for interaction are on the picosecond timescale. And this is all very important for time-resolved reflectance imaging, as well as for temporal frequency domain imaging. And intrinsic sources of contrast to absorption and scattering, both in the time domain and the temporal frequency domain, are linked to these absorption, scattering, and transport relaxation times. Okay? And so these are various metrics that are important. We'll see later on the importance of mu effective, which governs the penetration depth of light in highly scattering tissue, and some normalized constructs for scattering relative to total interaction. So I'm going to stop there, open it up for questions, and then we'll have time for a break. Okay, so any questions? Yes, we have a question there.
Actually, just 2 questions, but real quick, in your table,
Yes.
they're all supposed to be inverse millimeters?
No, so these are, mu A is in inverse millimeters.
Oh,
So if
okay.
you take the reciprocal of that, that's a length, right? And so that's why you see mu A is in the denominator. So all of these, the reciprocal of the mu A's give you, or mu S's give you length. Here again, let's take through the units. So we have a reciprocal millimeter here, so you get a millimeter on the numerator from this mu A. This is a velocity that's in the denominator, so you get a millimeter in the denominator, so the 2 millimeters cancel out, but you have millimeter per second. The second comes to the numerator, so you get times here. So all these are units time.
What about the scatter?
Same thing, right? Mu S also is in reciprocal length, so you take the reciprocal of that, you'll get millimeters here. So all of these are typical length values. These are typical absorption lengths, typical scattering lengths, and this is called the transport mean free path, all in units of millimeter. And these are what are called relaxation times. What are the characteristic times that a photon needs to travel in a tissue before it's absorbed, before it's scattered, and before it encounters a typical mean free path.
And these are all characteristics for a single photon?
For a single photon, you can think of it,
Okay.
as a single photon. Or propagation, these are lifetimes. You can think of them as lifetimes. What are mean lifetimes for absorption, scattering, or transport in the tissue. Other questions? And since a lot of people, I think, are working in the frequency domain, whether it's spatial or temporal frequency domain, if you take reciprocals of these spatial scales, you can kind of think about, in the spatial frequency domain, what are you probing? Whether are you sensitive to absorption versus scattering? If you're working in the temporal frequency domain, what are your intensity modulation frequencies? And are these modulation frequencies, how do they relate to characteristic absorption relaxation times? Typically, we're not modulating on these reciprocal temporal scales, but you are modulating either quickly or slowly relative to these absorption relaxation times. Other questions? Tom?
You had a question.
Hold on, let's wait for the microphone, if you would.
Going back when you were talking about integrating the radiance to measure the reflectance
Yeah.
of the surface.
Do you want me to go back to that slide?
Yeah, if you don't mind.
Okay, sure.
And I think this is just with my unfamiliarity with this idea of unit circle and directions.
Sure.
But I follow the idea that you want to integrate, photons going in that negative z direction, but you kind of lost me when you started talking about that dot product and a planar detector.
Okay.
Because I'm thinking you're measuring at a single point, right? So why does...
You're measuring at a single point. So, okay, so maybe I can use the screen here, the blackboard. No, that's wrong. I think the screen is hardwired into the projection, right? Or is it that? No. Richard, can you turn on the lights a little brighter? Screen up, thank you. I guess it's binary, either all up or all down. Can you also... yeah, that's great, okay. So if you just have a medium, you're looking at this light field coming up. I mean, if you have a camera, for instance, right, you have kind of a planar, I think of it as a planar detector, right? So let me just make the detector really large. Okay, so you've got this light coming here. You've got this light coming here. So all I'm doing with that dot product is that I'm taking the projection of that onto the normal, right? Because if it's grazing, let me just be very practical and not be if you have a solar collector on your roof, you angle that so that for most of the day when it's at high noon, your light rays are coming directly on the surface. So the sun is just as bright at sunset, but the light is grazing, and therefore you don't get as much power absorbed. And it's just a cosine term. So it's just the z dot omega is just a cosine term, so that even though you have a bright light coming out at an angle, so you have a huge amount of intensity coming out at this angle. If you had the same amount of intensity coming normal, that's going to contribute a lot more to your signal than this will, because ultimately you have to take the projection onto the unit normal. Does that answer your question? Does that make sense? No?
It's still a little unclear.
Okay.
I mean, because if you had a perfect absorbing detector, right, the angle wouldn't matter. Because those effects have to do with the refractive index and how much light gets reflected off that surface.
There's still the okay. I still think that you have to do the projection on the unit normal. At least that's how it's defined, the reflectance.
So it's only sensitive to photons that are on that normal.
It's not only sensitive, it's just you have a cosine theta term that modifies the contribution of light that are coming at oblique angles onto that detector. Yeah. Gordon.
I think a way to...
Yeah, please.
So maybe another way to think of that is when you look at your radiance, it's given in watts per square meter per steradian.
Yes.
And if your detector is at an angle, that square meter is changed by cos theta. So if your surface is at 90 degrees, then cos theta is 1, but if it's at 0 degrees, so if you're looking at if you're looking at a surface like this, essentially if you're looking from this angle, it has 0 area.
Yeah.
Whereas when you look at this angle, it has a much larger area, and I think that's where that cos theta.
So that same amount of power is actually distributed over a much larger area.
Yeah.
So that's another way to look at it. Okay. Thank you. Thanks, Gordon. Okay. More questions? People need coffee. Oh, yeah, we do.
Going to the, I guess, the scattering properties of the tissue,
Sure.
there was like a lambda, a reference wavelength.
Yeah.
So does that mean like everyone uses the same reference wavelength to
Unfortunately
make it
not.
comparable?
It's the choice of what you use for a lambda knot is not critical. It's just arbitrary. So I think in this paper, Steve Jacques uses 500 nanometers and that just tells you, it just tells you where is this factor going to be 1. And A is basically the value of mu s prime at that reference wavelength.
Okay.
So that's all it is, right? All of this factor is unitless. The only thing that carries units is A.
Okay.
And again, A is the value of the mu s prime at lambda naught. Some books use 1 micron, some use 500 nanometers. They're all over the place, actually. I saw a book that uses 1 nanometer as the reference wavelength, which makes no sense because but anyways. Tom?
While you're on the slide,
Yeah.
I'll have to go look at this paper, but do you know how he measured that fraction of Rayleigh scatters? Because, just looking at the units, is we can measure scattering as a function of wavelength, but you need more information to separate the size of the scatterers, right?
So he didn't actually measure the fraction of Rayleigh scatterers. What he did is that, as I understand, is that he had data that characterized the wavelength dependence of mu s prime over a large enough wavelength band, and then he fit it to this functional form and then derived this fraction of Rayleigh, right? So it wasn't a rigorous measurement. Yeah. It's actually a really nice paper, very rich with information on scattering properties. Okay, I think we need a break, some coffee, some stretching, restroom, and then we'll take 15 minutes. I think we'll get started at 5 to the hour. Is that okay? Great. Thank you. I know. It's a little slow, or no, it's a little.
It's ahead.
It's ahead. That's good. I'd rather be ahead than behind. You don't have to save or anything.
Yeah, I do want to.